So we've already learned that torque is essentially the rotational version of a force. It occurs when there's a force that is applied to some radial arm at a perpendicular axis. Up to now, we've looked at examples where the net torque on an object is zero, so that it does not actually rotate. We have balance on both sides. But what happens when we do have an unbalanced set of forces or an unbalanced torque? How then do we solve our problems? So let's first think about what we remember for forces. Remember that the net force of any system is equal to the mass of that system times the acceleration. We've already learned that certain variables can be replaced with a rotational version. What I mean by that is acceleration A is similar to the angular acceleration alpha of an object. And we recognize that force, a linear version, is similar to the rotational version torque. So I'd like to introduce the concept of a rotational version of a mass. When things spin, they're going to spin based off of a shape. And that's what we call a moment of inertia, I. An object's moment of inertia is dependent on its shape. Those shapes are outlined in various data tables. We'll find one on our formula chart that has a list of about 8. And the moment of inertia for every object is related to its mass and its radial axis squared times some fraction. And that fraction is going to notate in what way is that mass distributed around the object itself. So is that mass more in the center? Is it more to the outside? Is it an irregular shape? That's what that fraction is going to dictate. If we look at our formula chart, we'll see that a hoop, for example, has all of its mass located the same distance away from its center and on the very, very outside of its shape. And so a hoop has a moment of inertia of simply mr squared. Whereas something like a solid sphere has its mass evenly distributed, but more of that mass is being drawn towards the center where it's denser as opposed to on the outer edges. To account for that, we'll find a fraction in front of it, 2/5, and then the same mr squared. I've added the list of our common shapes that everything will be mostly based off of. Anything that's an awkward shape or not on this list is typically going to have a moment of inertia that is given to us. One of the things that we'll have to determine when we read a question is which of these shapes does an object most resemble? By that I mean if the problem talks about a beach ball. Well, a beach ball is a sphere, but it's hollow on the inside. So rather than being considered a solid sphere, we would think of that beach ball as being a thin spherical shell. But something like a baseball that is dense throughout would be more of a solid sphere. If we talk about a ring or a piece of jewelry, we'd have like a hoop. When we start talking about trash cans, they're cylinders and they're usually hollow, so we wouldn't see 1/2. We'd probably have an equation where they would tell us what this fraction is replaced with. But a solid cylinder, looking at some of the mass sets that we use on a regular basis, would be a good representation of one of those. I'll notice on my list that there's thin rod listed twice. One time it has a notation of a center, and once it has a notation of an end. Something that is a thin rod center would typically have the radius and the center point. I'm sorry, the pivot in the middle. So from here it rotates around in this fashion. Whereas a thin rod end would have that pivot point down at the base, kind of like a ladder, where it will rotate forward or backward in this manner. Just to make sure that everyone is comfortable with fractions, let's make sure that we recognize that a hoop has essentially a value of 1 in front of it, meaning that's a very large moment of inertia. whereas the thin rod center has a fraction of 1/12 in front of it, meaning that value will be very, very small by comparison. So again, the fraction in front of that mass radius component is going to dictate how much the moment of inertia of an object is and relative to a different object of a different shape. Most of us are pretty comfortable with fractions at this point, but I know that my students usually have an issue thinking about 1/3 versus 2/5, which of these is larger. So just to use that as an example, when comparing find a common denominator is one way to do it. So 15 is a common denominator. So I'm going to multiply this fraction by 5, and I'd end up with 5/15. To get this fraction with that same common denominator, I'd end up with 6/15, telling me that 2/5 is bigger. Another way I was taught to do it in elementary school was the idea of setting the two equal to each other and creating a cross product. And so if I multiply 2 times 3, I get 6. If I multiply 1 times 5, I get 5. I can see that this one is the larger one, so that fraction would be my larger fraction. So for that reason, I know that 2/5 is bigger than 1/3, meaning that the solid sphere has a greater moment of inertia than the thin rod end. So why is this important? Well, by knowing an object's moment of inertia, we can learn a lot about how fast it's able to rotate. Recall that we learned earlier this year that kinetic energy was 1/2 mv squared. This is really what we're going to call translational kinetic energy, meaning it's the kinetic energy of an object moving but not rotating. When we start to think of objects like marbles that rotate, we need to translate that equation for kinetic energy into a rotational form. Well, let's think about what we learned a second ago. All we're really doing is swapping out variables. So instead of an m, the rotational version of mass, we've now learned is a moment of inertia. And if I remember back from earlier in this unit, the rotational version of velocity v is really rotational velocity omega. Being as the velocity was squared in the initial equation, I'm going to make my omega squared. So this tells us about the kinetic energy of an object as it spins. So if an object is only moving along a plane, we would say that it has translational kinetic energy. If an object is only spinning, then it would have rotational kinetic energy. But sometimes we have objects that do both. So a tire, for example, will spin as it moves you forward. It has two forms of kinetic energy, and we'll need to account for both. In the same way that we had multiple forms of potential energy that we had to account for certain problems. We had gravitational potential as well as elastic potential. Now, the total energy that an object has to be accounted for. So when we have objects that have translational and rotational kinetic energy, what we'll find is something that is rotating. Part of that energy is being used for rotation, but part of it's also being used to move the object forward. And so as a result of that, the faster that something spins, the slower it moves linearly or tangentially. Or in other words, as my translational kinetic energy increases, my rotational kinetic energy would have to decrease in order to maintain a consistent amount of total energy, or vice versa. Here's a common physics question for us. We have a ramp, and on that ramp are various objects. Today we're going to focus on the cube, the disk, so a version of a solid cylinder, and a ring, or a hoop. Let's assume that all of these objects have the same mass and the same radius based on its center to its outer edge. If we release them all at the exact same time, which item do you think would hit the bottom first? Let's answer this problem using the physics that we've previously learned. energy. All of these objects are starting at the top of the ramp, meaning that they all are starting with gravitational potential energy. As they move down the ramp, they're going to pick up and finish with 100% of their energy being kinetic energy. Some of these objects are going to spin as they move down the ramp, meaning that as they rotate, we'll also need to account for having rotational kinetic energy as well as that downward tangential kinetic energy. The box doesn't easily spin, so it's only going to have translational or tangential kinetic energy. Earlier this year, we learned that we could create equations to tell us about how fast something was going to go based off of its position and height relative to that starting point. So let's see what that might look like for our various objects that we have here. So our cube is going to start with potential energy up at the top of the ramp. And by the time it gets to the bottom of the ramp, all of that energy will have become kinetic energy. Because it doesn't rotate, it would all be translational kinetic energy. So we could figure out how fast it's going by substituting our potential energy equation, mgh, and setting that equal to our translational kinetic energy equation, 1/2 mv squared, where we learned earlier this year that our velocity would be equal to 2 times the height in gravity with the square root of that whole factor. But how does this change when we add in the idea of rotation? Our hoop would still start with potential energy at the top of the ramp. But now when it finishes, it has kinetic energy in two forms. It has translational kinetic energy as well as rotational kinetic energy. How does that affect its speed? Does that make its speed faster or slower overall? The equation for potential energy hasn't changed. It would still be mgh. Our translational equation for kinetic energy, still 1/2 mv squared. And we'll bring forward the kinetic energy equation that I created earlier, where we've swapped out the mass for a moment of inertia and velocity for an angular velocity. I have a lot of various terms here, so I'd like to expand on this idea and try to find some common terms. I know that my moment of inertia of a hoop is equal to mr squared. I can bring down the other components, and I'll notice that every term, again, has mass in it. So I can actually cancel out the mass component of this equation to simplify my overall setup. Now there's one more place that I can simplify. I learned earlier that the tangential velocity of an object was related to the radius of that object and its angular speed. I have similar terms right here, but they're squared. What this means is that if I have a radius squared and an angular velocity squared, then I really have a tangential or linear velocity squared as well. So now I'll rewrite my formula using common terms, having substituted in for those variables. And now I have an ability to simplify my equation one step further. I have velocity squared and velocity squared. So half plus half, what I really have now is g times h is equal to v squared, or the velocity of the hoop is equal to the square root of g times h. The velocity that I have here would be less than the velocity that I had for my cube. So my hoop will actually travel down the ramp slower than my cube will because it has the benefit of this extra factor of 2. So how would this work for a disk or, in effect, a very, very thin solid cylinder? Because really that's all a disk is it's a circular shape with a small amount of extra mass associated with it. So let's have you try to figure out what the velocity of our cylinder will be. Keep in mind, we know that it's starting out with potential energy initially at the top of the ramp. It will move down the ramp in a linear form, and as it's moving down the ramp in a linear form, it will rotate. After some algebra, you should hopefully learn that the velocity of the cylinder at the bottom of the ramp will be the square root of 4/3 times its gravity times the height that it started at. So the cube's velocity was the square root of 2gh, and our hoop's velocity was the square root of gh for its velocity. 4/3 would fall between these, greater than 1, less than 2, and so it would come in second place, cube first, disk second, and our hoop or our ring third. Based off of these final equations, we can see that velocity is dictated by gravity and height, as well as the shape or the moment of inertia of that object. As we learned earlier this year, mass does not dictate how fast the object will go. So let's recap. We have two ways that torque can be found. Torque is related to the force times the perpendicular radius, and we now also have that torque is equal to the moment of inertia times its angular acceleration. I find that it is quite easy to use our force and radius equation when we have objects that are at static equilibrium, meaning that they are balanced. But when things start to have dynamic equilibrium, or when they start to turn at a constant rate or a non-constant rate, we really have to consider that moment of inertia. When they're turning at a constant rate, we find that it's fairly easy to think about our conservation of energy equations. Conservation of energy applies when we have no work or no changes in the amount of energy due to those outside forces. But what happens when we do have outside forces that start to affect our objects? What we found earlier this year with our linear motion was that when conservation of energy didn't hold true because of having these work components, we had to think about a different form of conservation. We thought about the conservation of momentum, where momentum was conserved even when we had two separate systems collide with each other and exchange energies. So how does momentum look when we're talking about rotation? Let's think about our old linear version of momentum. Linear momentum was the letter P, and it was equal to mass times velocity. All we're going to do is swap out our linear components for our rotational components. So we know now that the rotational version of a mass is a moment of inertia. We know that the rotational version of velocity is rotational velocity. And so we need a variable to represent having rotational momentum. And that variable is going to be represented by the capital L. This equation can be very useful for collisions, as well as for when objects start to change shape in the middle of a scenario. For instance, if you've ever seen figure skaters, when they start to spin, they'll take their arms and bring them very, very close into their body. And as they bring their arms super close into their body, their rotation starts to increase faster and faster and faster. And then when they want to pull out of that spin, they take their arms and they move them back outward away from their body. What they're doing here is changing the moment of inertia that they have. And as a result of that, they're changing the velocity that they have. Because in order to conserve momentum, as the moment of inertia increases, the angular speed or the rotational speed would have to decrease in order to maintain or conserve that momentum. Since our skater here has a larger radius compared to when our skater has her arms pulled in, they have effectively changed their moment of inertia. By having that larger radius, this skater will have a larger moment than this skater. But this is the same skater overall. All they've done is change the positioning of their arms. So by doing so, in order to maintain that same amount of momentum, our skater with their arms out wide will have a very small rotational velocity, whereas pulling my arms in will increase my rotational velocity. I'm still balanced, or I've still maintained the same quantity of my momentum. We might ask ourselves, what was the outside force that did work to have our skater pull their arms in? And in that sense, there's not an outside force acting. Here it's really almost more of an internal force. But the skater had made a decision. They had to do work. They had to convert energy themselves to pull their arms in to that position. And so that's the form of work that we're talking about, is the conscious action to change the shape of my body is in fact work. Both versions of the skater have the same momentum, but do they both have the same kinetic energy? Well, for that, let's think about our kinetic energy equation. They are not moving forward necessarily while they're doing their spin. They're staying in place, and therefore they have rotational kinetic energy. Keep in mind that rotational kinetic energy is 1/2 I omega squared, where the body position on the left has a large moment but a small angular velocity, compared to the body positioning on the right that has a smaller moment of inertia with a larger angular velocity. Do they balance out? Are they still equal? No. Keep in mind that our angular velocity has a square factor associated with it. For that reason, having a larger angular velocity that will then be squared will result in having a greater amount of rotational kinetic energy than our left-hand positioning.